Welcome to my video course on engineering FRMCS. I am absolutely thrilled to guide you through the intricate architecture of the future railway mobile communication system today. Our overarching engineering goal here? It's figuring out exactly how to achieve ultra-reliable, continuous connectivity for high-speed moving trains. Because let's face it, in modern rail operations, a data dropout isn't just an inconvenience, it's completely unacceptable. We are moving way beyond the legacy GSMR systems. You know, that older 2G standard we traditionally relied on. To do that, we literally have to engineer a communication matrix that is dynamically adaptable, highly secure, and just incredibly resilient.
Here is our syllabus for today's lecture. We are going to cover 5 main areas: architecting bare flexibility, understanding multi-access, the mechanics of multipath, operating heterogeneous access networks, and finally, implementing the multipath function. Let's jump right in. Section 1. Architecting bare flexibility. Okay, let's dive into this. Our very first core concept tackles what is honestly the most critical engineering problem in railway communications right now: keeping a flawless connection across moving infrastructure. I mean, think about it practically. A train isn't a stationary office building plugged into a nice fixed fiber optic line. It's essentially a massive hurtling data center. It's blasting through deep tunnels, remote mountain ranges, and dense cities, weaving in and out of coverage zones at hundreds of kilometers per hour. So to solve this immense challenge, we use a strict architectural principle called bare flexibility. By definition, this is the capability to utilize available transport and access networks across the administrative domains of an FRMCS operator or a public mobile network operator. What does that actually mean for us? Well, it means we are completely done relying on a single dedicated railway radio network. Relying on just one network creates a single point of failure, and that is a massive liability. Instead, this modern architecture dynamically grabs onto every available transport network around the train. If one network starts to degrade, the system instinctively flexes and hops to another, ensuring the connection literally never breaks.
To pull this off, bare flexibility taps into what we call heterogeneous access networks. We start with our primary baseline layer, the RMR spectrum, our dedicated 5G railway mobile radio bands. But then we supplement that by integrating public MNOs. Yes, the exact same standard commercial 5G and 4G networks you use on your smartphone every day. Plus, say the train pulls into a station or a maintenance depot, it might seamlessly hand over to Wi-Fi, which in telecom terms we simply call a non-3GPP terrestrial network. And finally, for those truly remote middle-of-nowhere coverage gaps, the architecture even integrates non-terrestrial networks, like satellite connectivity. By stacking all these diverse layers together, we build a totally impenetrable web of continuous connectivity.
Section 2. Understanding multi-access and multipath.
Now, we really need to clearly distinguish between the two primary engineering capabilities that make this bare flexibility a reality. Precision is everything in telecommunications, right? So let's compare how these operate. Multi-access happens way down at the radio technology layer. It's the simultaneous use of standard 3GPP and non-3GP radio access technologies, or RATs for short. Basically, it's one single device speaking different radio languages at the exact same time, like communicating over 5G and Wi-Fi simultaneously. Multimodem, on the other hand, is coordinated slightly higher up at the user equipment layer. It involves the coordination of at least 2 separate user equipments, think 2 distinct physical modems, serving the exact same onboard application in parallel. So one modem might be talking to the private railway network, while a completely separate modem talks to a public network, both working together to deliver the same data stream.
Section 3. The mechanics of multipath. Let's transition our focus specifically to multipath now, because this is the absolute key to continuous onboard connectivity, especially when we're talking about mission-critical, life-or-death train operations. We deploy multipath across a highly specific set of use cases. We use it for application-specific data path selection. For instance, critical driver command data goes securely over the protected RMR spectrum, while heavy passenger infotainment data is simultaneously pushed over public Wi-Fi. It gives us instant fallback during a link failure and extends coverage at those tricky edges of cell towers where signals normally fade out. But the real game changer here, the absolutely crucial mechanic, is resilience through packet replication. Picture this: the exact same IP packet is duplicated and fired off simultaneously over 2 completely different data paths. Whichever packet gets to the destination first is instantly processed, and the lagging duplicate, it's just dropped. This is a brilliant piece of engineering that guarantees ultra-reliable communication with near-zero latency interruption.
Section 4. Operating heterogeneous access networks.
Now, what's really interesting about this slide is how the multipath function physically bridges the whole system together. On the left side, you've got the onboard systems of the train itself, and on the right side, representing the trackside infrastructure, is the core FRMCS domain. Notice how the multipath function sits right in the middle as a critical bridge on both ends of the connection. It's essentially the grand conductor of this entire matrix. It orchestrates parallel data paths simultaneously through the dedicated FRMCS network at the top and a public MNO network below, managing these entirely different core networks and flawlessly reuniting the data on the other side.
And here is a deeply crucial engineering truth regarding this topology: application transparency. The actual applications running the train, whether that is the European train control system, a live video surveillance feed, or telemetry data, they have absolutely no clue that this incredibly complex, multi-network routing is happening beneath them. All that complex decision-making, the packet duplication, the instant hopping between 5G and Wi-Fi, it is completely invisible to the railway application stratum. The application simply asks for a connection, and the multipath function abstracts the whole shebang away, consistently delivering a flawless, unbroken connection.
Section 5. Implementing the multipath function. So, how does it actually manage these invisible data flows, moment by moment, at hundreds of kilometers an hour? It boils down to 5 precise control capabilities built into the system. Step 1 is data path selection, where the system dynamically evaluates network policies to pick the best initial path. Step 2 is QoS control, where it strictly conveys quality of service requirements to the underlying networks to ensure bandwidth is locked in. Step 3 is data path switching. Say a train blasts into a tunnel and loses public MNO coverage, the function instantly switches the data flow to the dedicated RMR network. Step 4 is data path splitting, distributing packets across multiple networks to vastly boost overall capacity for heavy tasks. And finally, the absolute pinnacle of operational reliability, data path duplication, replicating those vital packets across multiple networks simultaneously so a dropped signal never, ever results in a dropped command.
So what does this all mean? I want to leave you with this final provocative thought. When we perfectly engineer bare flexibility, multipath, and multi-access, we are doing so much more than just upgrading a train's radio. We are literally building the foundational nervous system required for true automatic train operation and fully remote driving. Without the absolute guarantee that a command will reach a train regardless of momentary network failures, autonomous rail operations remain just a theory. But with the highly resilient architecture we've explored today, it becomes an imminent reality. Thanks, we can see you next video.